Hello, dear students. Welcome to the channel and very much welcome to this playlist in which we are discussing about the transmission line modeling and performances. Up until now, we have seen different types of transmission line. We have seen generalized constants or ABCD parameters for all those types of lines. We have seen different types of representation for a transmission lines like N T modeling or pi modeling. We have seen different methods for the calculation of sending and receiving end voltages. We have seen calculation of voltage regulation and efficiency for all the types of transmission lines. And in very previous lecture, we have seen tuned power lines and the power through the transmission lines, how we can give the formulas for that. And continuing that discussion, I want to discuss about the receiving and power circle diagram today. So to understand this particular video or this particular lecture, you must need to understand the previous video or previous lecture. So if you haven't checked that out yet, please click on the I button above, or it will be flashing on the top right hand side corner of your screen, so you can watch the previous video from there. I will be providing the link of that in the I button. So assuming that you have already seen that, I would start today's discussion. So firstly, about the power circle diagram. So why do we do that? Why do we plot the power circle diagram? You have seen a lot about, you have heard a lot about power circle diagram in power system, right? So why do we do that? So because the aim of plotting power circle diagram is to check it or find it the performance of the transmission line and the complex power at sending end and receiving end of the transmission line. So you want to find the complex power on either of the sides of transmission line. You must plot a power circle diagram. By that, it not only provides you that quantity, that particular quantity, but it also provides you with other important aspects and other important quantities of power system as well, right? So firstly, the apparent power of my system, or apparent power of the line, can be given as for the sending end can be given as PS plus JQS, as you can see here. And it is represented by this formula as we have seen here, and we have derived this formula in the very previous lecture, so I'm not going to repeat everything here again. The apparent power on the receiving end can be given by this formula, PR plus JQR, and the formula for that is given as here. So what is complex power here? So complex power is actually the sum of two phases. uh, Real component of those phasor represents the real power, which we indicate by P, and imaginary component indicates the reactive power, which we indicate by Q, right? So we can plot this sending end apparent power and receiving end apparent power in a graph, XY graph. So what we will do, we will take true power on horizontal plane, or x axis, and on the y axis or vertical plane we will take the reactive power, right? And the transmission lines which we are using are usually operated with constant sending and receiving end voltages, right? So one component for each both sending end and receiving end power will be fixed phasor, like it will have a constant magnitude, and it will have a constant or a particular fixed phase angle, right? And except for this component, the other component which will be having will be the phasor of constant magnitude, but its angle will keep changing, right? The magnitude will remain constant, but the angle will be variable. And when your angle is variable but your magnitude is constant, what will happen? You will form a locus, right? So you will form a locus of your sending end and sending end and reactive end apparent powers. So it will look like circle. It will you will draw a circle which will come from the tip of the constant phasor and throughout the whole radius, right? So the circle which we will draw with receiving end powers, receiving end apparent power, which will consist both true and reactive power, we will draw it at as the horizontal axis, right? And on the vertical we will be drawing on the vertical coordinates will be called receiving end power circle diagram. So coming again to the formulas, we can represent the receiving end active and reactive power component with these formulas. So we can get PR, it will be equal to A by B VR square cos beta minus alpha. Ignore this plus sign. We are actually plotting receiving end true and reactive power, which means we are plotting PR and QR here. So what we will get PR plus A by B VR square cos beta minus alpha, which will be equal to VS VR by B cos beta minus delta. By the way, this formula we have derived in the previous lecture, in the previous video itself. So uh, if you want to know how did it came, you can check that video out. Then we have the formula for QR or reactive power. It will be equal to QR plus A divided by B VR square sine beta minus alpha equal to VS VR divided by B sine beta minus delta. Now what we will do, we will take both of these terms, we will add them, and we will square them. So when we will do that, we will get, we will get something like this. See here, we will have this term, the whole square of this term plus whole square of this term, and here we will apply the formula of a plus b whole square is equals to a square plus 2ab plus b square, and you will get PR plus a divided by b VR square cos beta minus alpha whole square plus QR plus a divided by b VR square sine beta minus alpha whole square. And on the other side, when you add both of these components, what you will be getting, you will be getting VS VR by B, and again VS VR by B, so you will get VS VR by B whole square, or you can even uh, put the square independently if you want to, because it is nothing but multiplication and division, so you can do whatever you want with the squares. Then you will take cos and sine, and you will take cos square beta minus delta plus sine square beta minus delta. Cos square theta plus sine square theta is always equals to 1, so this formula will be 1, and you will be left with VS square plus VR square divided by B, right? Then the coordinates of the center of circle and the radius of your circle. So to obtain those coordinates for the center of the circle and radius of the circle, you can find it from these formulas. As you can see here, for x coordinates you will have minus a by b VR square cos beta minus alpha, which is basically this formula here. And for y coordinates you will have minus a by b VR square sine beta b minus alpha, which is again basically this formula here. So for x coordinate of the circle you will get this formula, for y coordinates this formula, and the radius of the circle will be this formula, VS square VR square divided by B. So if you pay close attention to this big formula, this whole formula, so it resembles the it has a huge resemblance with the formula of a circle, right? X square minus y square is equals to r square. So basically we are coming to this. Now let's come to the construction of my power circle diagram. How will it look like, and what we will do with it. So first what we will do, we will take whatever the suitable scale is at the center of the circle, and we will plot it first, and we will call that center of the circle as n. So you can see here you have center of the circle n, and you will plot this first, right here. Then you will form the center of the circle. The arc will be plotted with the calculated radius, right, the center of the circle. So uh, what you will do, we will plot the load line, which is given this as OP. This the load line, which is resemble which shows SR, receiving end apparent power. And you will plot it at angle phi r. As you can see here, the angle will be phi r, right. What it is doing, so it will cut the circle at angle P. See, at this point it is cutting the circle, and then a perpendicular will be plotted on horizontal from your P axis here, as we have did, and we will call it Q. And now this OQ and OP, what is it showing? So it is showing nothing but your active and reactive powers, right. It is showing your active and reactive power. So here you are having active power, here you are having reactive power, and this is the hypotenuse, which is showing the apparent power. So it is basically a your power triangle, you can call it a mini power triangle in here. Now if Vs and Vr are phase voltages, as you can see, we are having Vs and Vr for phase voltages, then these powers will be per phase powers. And if Vs and Vr will be line voltages, then these powers will be three phase powers, right. But depends on your Vs and Vr. And what will be the value of Vs Vr by B? It will be the radius of your circle, right. Multiplication of Vs and Vr, and you will divide it by B, and you will get the radius of your circle, right. So to determine the maximum power, what you will do, you will draw a horizontal line from center of the circle, which will intersect your vertical axis at some point L, right. You will draw a vertical line which will intersect your vertical axis at some point L, at this point L, and it will intersect the circle at some point M, this point. And this distance, this LM distance, will be the distance which represents the power at the receiving end. So this is the power at receiving end, right. So you can find the receiving end power from circle diagram with this way. First, what you will do, you will plot N, then you will get O, then based on the power at angle phi r, you will draw OP, you will get this here perpendicular point Q, then you will get OQ and QP, and based on that you will find active and reactive power. And then you can, from your center of the circle point, you can draw a line, and based on that you can find L and M, right. And from this line LM will show you the power at a receiving end, right. Again, that was your receiving end power circle diagram. Now coming to the methods of voltage control compensation of a transmission line. So see, equipments which we use mostly are rated for some certain voltage, right, with some your permissible band of voltage variation, right, some plus or minus 5% most of the times, for in case of modern vehicles, modern components, sorry, not vehicles. So the transmission lines which have to transfer power with the voltage drop less than 10%, right. So most of the loads which are connected to the system will absorb the lagging power, lagging VARs to be precise. and the flow of reactive power in a transmission line will cause some voltage drop. And what it will do, it will also increase your I square R losses, right? So the maximum VAR transferred over one line will be fixed, right? It will be fixed by voltage profile only. So at the time of peak load, what will happen? The VR demand of your load will exceed the maximum VR limit which is specified by your voltage profile. And when such thing happens, because of this, your system voltage at some of the buses will become lower than the nominal voltage. And your system voltage becomes lower than nominal voltage, the additional equipment which is connected to the system will start to generate the lagging VAR, right? In order to meet your requirement of reactive power of your load, right? So that the voltage can be maintained on different buses within specified limits. So for the case of light loads, what will happen? This lagging VAR which is produced by the lines are very much compared to requirement of the loads, right? And because of that, what happens, this VR becomes surplus VR, and this surplus VR must be absorbed by additional equipment, any additional equipment, in order to maintain your voltage profile within the limits. If that doesn't happen, then the system voltage at some of the buses will become higher than the nominal voltage, and because of that, this additional equipment which we are using for absorption of additional VARs, we will call those additional equipment reactive power compensation equipments or reactive power compensation devices, right? And these equipments will are helping us in reducing the compensation of reactive component of current. It also reduces the copper losses in your system. It maintains the stable voltage profile. Basically, that's the primary motto of ours, so it will provide that operation. It will also use for improvement of power factor, which we have shown in the previous playlist of this subject as well. And also it reduces the kVA loading of generator and the circuits, right? So basically what we are doing, we are just preventing the system voltage in some of the buses from becoming higher than the nominal voltage, because it can cause a lot of damage to your system basically, right? So among these methods of reactive power compensation, the first method we have is called static compensation. So in the static compensation, we have some equipments like shunt capacitors, shunt reactors, series capacitors. So we will see one by one. First, let's see the shunt capacitors. So these shunt capacitors are connected across the inductive load to supply part of the reactive power which is required by the load, and thus the reactive power which is transmitted at the load is reduced and voltage across the load is maintained within the specified limits. So what happens when the small bank of capacitors up to let's say some certain hundreds of kVArs are connected at your premises, consumers premises, what will happen? The capacitor bank of few hundred thousand kVArs are used in small distribution substations, right? And with large ratings are used in the large substations. So based on the substations size, substations rating, you will use a small kVAr capacitor or a high kVAr capacitor, shunt capacitors, right? And where will you connect where will you connect uh, this capacitors? So let's call it capacitor bank. Okay, so this capacitor banks will be connected in either star or delta manner, and they will be permanently connected to your system only. So capacitors, when switched on or off based on the demand of your system. So if your system demands the capacitor to be on, it will be on. If system demands its demand is to turn off the capacitor, it will be off, right? So during the peak load conditions you will turning them on, and during the light load conditions you can turn them off. And you can do this switching either manually or automatically. You can set the switch for it. You can automate it based on your requirement and resources available. Then the second we have shunt reactor. So what happens in the case of shunt reactor? So we use shunt reactors again for the same purpose, to absorb the lagging VR generated by the line during the light load conditions. And the reactor which we use are mostly coreless type, or gagged core types, you can say. So this coreless reactors will be used for large rating and voltages. And the tapped saturated reactors can also be used, right? Like reactors saturated selected voltages within plus or minus 10% of nominal system voltage. So when saturated VARs absorbed by the reactors will change rapidly for small changes in voltage. So if there is a small change in voltage, the saturated VRs will absorbed by the reactor. Okay. The third one, which is a series capacitor. So these series capacitors are connected in the series with the line, not a rocket science, as its name suggests. And it will reduce the inductive reactance of the line, and by doing that it will also reduce the voltage drop, right? So basically it helps us increasing the maximum power which is transferred to the system. It also reduces the power angle for a given amount of power transferred, right? And remember, the lesser the power angle or load angle, better your system will perform, right? In increased loading conditions it will also help. And in series capacitor, in series compensation, when we add a capacitor in line, it will reduce the effective line reactance. And by doing that you can improve the performance of power system. Like what you can improve, you can your voltage drop in lines will be reduced. It will also prevents the collapse of voltage, which happens if it is not present, right? It also increases the steady state power transfer, and it increases the transient stability as well, right? So that was your series capacitor. The third one, second one is static var compensator, SVR. So SVC, you can say static var compensator, or SVC we call it. So this SVC consists of fixed capacitor banks, which we saw just before, or you can call you can see parallel capacitor bank, and they are switched by reactor bank in parallel, right? So what it does, it draws the lagging or leading reactive power from the line based on the requirement of your system, right? So what will happen, a reactance will be connected in parallel with a line, and it will draw reactive power. So it is negative if reactance is capacitive, and it will be positive if my reactance is inductive. And by doing that, what it does, it regulates your voltage, it improves the stability, it provides you controlled voltages, or it also prevents the over voltages, right? And also it reduces voltage flickers, right? The flickers which takes place when you suddenly connect a heavy load with your system. So it also prevents the flickers. So here in this figure you can see the circuit diagram for static var compensator. We have thyristors, two thyristors we have taken. You can call it a pair of thyristor. We use them, but they are not in parallel, they are in anti-parallel. In anti-parallel formation, they are connected, so that we can switch on the reactor or capacitor, whatever you have connected, uh, in the stepwise control, right? So if the circuit is designed to adjust the firing angle of your capacitor or reactor, both you have connected both of them, so unit will act as a continuous variable in the power circuit. And using this thyristor control capacitor or the capacitor, the inductor bank will be changed accordingly, right? So both reactor and capacitor are making adjustment based on the requirement of your system here. And that's pretty much of your static var compensation. Third point is the synchronous compensator. So this is something what we have seen back in when we discussed about the synchronous motor, synchronous machine, and we have discussed about the power factor control of in synchronous machine. So we have discussed it, so I will not take too much time discussing it. So let's start. First, we also call it synchronous phase modifier, or we basically it is nothing but synchronous motor with no mechanical output, so you can also call it synchronous phase modifier. And what it does, it takes some real power and it supplies its real power, and it supplies this to its losses. And these machines are provided with some adjustable excitation to provide necessary compensations, right? So this synchronous machine will be provided with lagging var when in the case of over excitation, as we saw earlier, and leading var when your system is under excitation. So by doing that, the reactive power can be provided by synchronous machine and can be continuously varied in magnitude and direction, both of them, right? So here you can see it is a synchronous condenser which is connected to your load bus, and the current, this current IC is the input current for your synchronous machine. This is your synchronous machine, and the formula of IC can be given as this VR minus EG, which is EMF generated by synchronous machine, divided by root 3 XS, right? And XS is your reactance here, right? And what is VR? VR is the load connected here, the potential or voltage of connected load, right? Again, the reactive power for this system will be given by J into QC is equals to root 3 VR minus uh, IC star. And we have derived the value of IC earlier as well, but based on that we will just substitute the value of IC here, and we will get JCQC is equals to root 3 VR and value of IC, and simply multiplying it inside this root 3 and root 3 will cancel out each other, so we will have VR EG divided by XS into, we have VR square because 2 VRs here, and we will have divided by XS square, right? So that will be your QC. So what will happen here in condition of over excitation, this EG, the induced EMF, will be more than the receiving end voltage VR, right? It will be more than this. And in such cases, what is happening, the QC will be positive here, right? If this is more than this, and VR is getting subtracted here, VR square by XS is getting subtracted here. So what will happen, the value of QC will be positive, and the compensator will deliver the your var in peak load condition, right? But in the case of under excitation, your induced EMF, this EG, will be less than VR, and when the value of EG will be less than VR, what will happen, this multiplication will be less than this, right? And in such case, what will happen, the value of your QC will become negative, and when your QC will become negative, then the compensator will use the VR during the light load condition, right? So a transmission line will require lagging VR during peak load condition and leading VR during the off peak condition, or no peak condition. And because that the synchronous compensator will be uh, suited very well for the regulation of voltage, as well as it can supply both lagging and leading VARs. uh, if not synchronous compensator, we can also go with static var compensator, which is also very much helpful. So that was the methods for voltage controlled compensation in transmission lines. And with this, we are ending today's class. If you have any doubts, any queries related to this class or this playlist, most probably this will be the last video of this playlist. So if you have anything related to this class or this playlist, please feel free to mention in the comment section below. If you have any feedback for me, also please feel free to mention in the comment section below. I will try to answer you as quick as possible, as many as possible. So I will be seeing you next time with a new lecture and most probably a new series of lecture, new playlist. Till then, thank you very much for listening and take care of yourselves.